Hello and welcome to the video lecture for topic 26, Organic Redox Part 2. So, a while back, earlier we saw how to convert a alkene to an epoxide via a two-step process. We saw how we could first take an alkene, we could treat that with Br2, Br2, and water, and that would give us our halohydrin. Bromine on one carbon, OH on the other. If we then took this and treated it with base, so I'm going to use sodium hydride here, that's going to cause deprotonation of the alcohol to generate a good nucleophile, which will attack this electrophilic carbon and ultimately give us an epoxide. Being that we are organic chemists and we're always on the lookout for a more efficient way to get the job done, we've been fortunate enough to develop a new way or a superior way of making epoxides all in one step. And so what we do is we start off with an alkene, and we treat that with a reagent known as MCPBA. So I'm going to draw the reagent first, and then from there we'll talk about why it has that name. So this reagent here is abbreviated MCPBA. That stands for metachloro. And that's because when you have a benzene ring and a substituent is, two substituents are only separated by one carbon, this is known as a meta-type substitution versus an ortho or a para substitution. So we have a metachloro peroxy benzoic acid. Now, parsing out the rest of the name, peroxy acid, peroxybenzoic acid, that's covered really nicely, in the POGO worksheet. So I'm not going to get too deep into it there. What I am going to do here, though, is show you the arrow pushing for how these two reagents come together to form an epoxide for us, and we're going to track some oxidation state numbers as we move along. Well, really, we're only going to track one oxidation number, and that's the oxidation number of these alkene carbons. They're going to start off as a -2 oxidation, okay? When we have hydrogens, It's going to be a -2 when we have hydrogens. So for our example here, how would the arrow pushing look for this reaction to proceed? Now, normally, I'm a big believer in you can only push about 2 to 3 arrows in a single step. Our MCPBA reactions get to violate this rule. We actually get to push 4 arrows and get the entire reaction done in one shot. So because we're doing all of our bond making, all of our bond breaking simultaneously, this is going to be a concerted reaction. And it goes through, it results in a syn addition. Okay? So how does that arrow pushing look? Well, we do a little bit of a Diels-Alder type of arrow pushing, Or what we saw when we were initially adding X2, where the electrons in this oxygen-hydrogen bond, those are going to go to make a bond with one of the alkene carbons. Pi bond, of the alkene is going to go to make a bond to that oxygen atom. Simultaneously, this oxygen-oxygen bond is going to break to form an oxygen-carbon double bond, and our existing oxygen-carbon pi bond is going to break to remove that hydrogen atom, or to grab that hydrogen atom. The end of this process, what we've formed, if we track our arrows, is we have our epoxide is formed, and we have a syn addition, right? Both of those carbon-oxygen bonds have to be on the same face, right? They're on the same side. And if we look at if we track what happened to MCPBA, we'll see, and now here I'm going to hold everything constant and just track the movement of my electrons. Here's that carbonyl oxygen. This is now an OH, where that hydrogen was, and that's where my carbonyl is. I have taken my peroxy benzoic acid and made it just into a benzoic acid. And if we track the oxidation state of this carbon atom, we started at a -2. Over here in our alkene, we end up at a -1. Here in our epoxide, that carbon atom has formally lost an electron. In fact, each carbon atom of the alkene loses an electron. This is overall an oxidation process. If you track what's happening here, you'll see, and you do your oxidation states, you'll see that this is also an oxidation process. And it's good for you to know where really does that oxidation occur, but I'll leave that as an exercise that you can do on your own time. Okay, so that's our first reaction for topic 26. And really, topic 26 is all reactions and mechanisms. We got a bunch of them to get through, but it won't take us too long. All right, so our first reaction, MCPBA to make an epoxide from an alkene. I'm going to clear off this board, and we're going to see how periodate can take a diol and convert that into some carbonyl compounds, another type of oxidation we're going to see. Okay, so in topic 25, we saw how we could use osmium tetroxide, T-butanol, T-butyl peroxide, and sodium hydroxide to convert an alkene. So here we're just going to start with an alkene, right? We're going to use osmium tetroxide. We have our T-butanol. We have T-butyl peroxide. And we have sodium hydroxide. All together go to form a cis diol. Diol where both of the OHs are on the same face of that cyclic system. Well, we can take this one step further, and if we treat this with a reagent known as sodium periodate, so Na plus, and our periodate, here's our iodine, we're going to have, 1, 2, 3, 4 oxygens off of that. So that oxygen gets a negative charge. These oxygens are all neutral. And our iodine is at an oxidation state of 7. Right? So this is sodium periodate, NaIO4. Right? Our charges are balanced in our salt, and we know the oxidation state of our iodine 7. Now, when we treat this, right, when we take these two, this diol and sodium periodate, we're actually going to be able to affect something very similar to a ozonolysis with a reductive workup. So we're going to see how the end products are an ozonolysis with a reductive workup. And just to really bring that home, I'm going to modify this slightly. I'm going to put a methyl group there, right? And then that gives us a real good ability to see how we get the same types of products as an ozonolysis from a reductive workup. So the first step of arrow pushing is that this oxygen atom is going to attack into the iodine, which is going to break one of these iodine-oxygen double bonds. I'm going to stop drawing the sodium atom. It's not going to do anything, but it's just one less thing we have to have on the board. So we'll make a little space that way. So we get to this intermediate. One, two. Need to keep track of all my oxygens here. Okay, we get to this intermediate, which has that oxonium type oxygen there. And one of the reasons I like this mechanism is because we get to start breaking a lot of the rules and get away with it in this mechanism, right? It's one of those special circumstances that lets us break some rules. And any chance I get to break some of the rules that we've developed, I really want to highlight that. So here we have 1, 2, 3, 4 atoms away. Normally we can't do a deprotonation 4 atoms away. But luckily, iodine is just big enough, and this oxygen is pretty far away from that iodine. This oxygen is pretty far away, that we can actually have this 4-membered state to go ahead and deprotonate that oxonium. That hydrogen gets transferred from the alcohol oxygen onto our iodine oxygen. We are still at an oxidation state, though, of 7 here. All right, that's going to take us to this intermediate. There's my iodine. Here's my other OH on a wedge. My methyl group there is on a hash. And now I've got an OH there. It's done its job. There's one of my double bonds to oxygen. Here's my O-, keeping things copacetic with the sodium I've stopped drawing, but is still around, right? At this point, my other alcohol oxygen is going to do the same thing. It's going to attack into the iodine, breaking one of the iodine-oxygen pi bonds. That's going to take us here. And we get to break that 4-membered ring rule again, deprotonate that alcohol, which gets us to our next intermediate. I know I'm moving a little in a slightly odd direction, but that's all going to make sense here at the end. So here now, this oxygen is connected to our iodine. This oxygen is connected to our iodine. There's my methyl group down, and I've got there's one of my OHs. Here's that double bond to oxygen. I've got another OH, and I've got an O-. Very crowded around that iodine. We're very fortunate that it's such a big atom that it can accommodate all of these things attached to it. Now, finally, what ends up happening is we go through a little ring breakup. This 5-membered ring between the iodine, the 2 oxygens, and the 2 carbons is going to break apart to give us our final products. And the arrow pushing for this step looks like this. So here we're going to push to make a carbon-oxygen double bond. This carbon-carbon single bond is going to push to make a carbon-oxygen double bond. And finally, this iodine-oxygen bond is going to break to dump a couple of electrons onto iodine. And that's going to give us our final product. Make this arrow a little bit shorter, give us a little more space. That's going to give us our final product, right? Which is going to be here now. I've made an aldehyde on that side. I'm exaggerating that bond just to give myself a little bit of extra space. But if you see, we've made this carbon to oxygen, a carbon-oxygen double bond. That's going to make this carbon sp2 hybridized, which means that I don't have stereochemistry anymore, and I've made an aldehyde and a ketone. That would be the same result if I had taken this starting alkene and done 1 ozone followed by 2 dimethyl sulfide. Excuse me. Dimethyl sulfide. The convenient thing is that I can combine all of this, my osmium tetroxide situation and my sodium periodate situation, all into a single reaction and get this result as well. So we can do it this way, or we can do OSO4, T-butanol, right, NaOH, NaOH and NaIO4. If we take this combination together, right, this is all done in a single reaction. Ozone is, it's a single reaction, but it's done in 2 steps, right? So either one of these 2 sets of conditions get me to this situation. Okay, so that covers sodium periodate. The next thing that we really need to look at is to look at what's called the Jones oxidation, right? And so we're going to come back and take a look at that real quick. Luckily, that's one where I'm not going to have a mechanism. All right. Okay, so the next oxidation we're going to look at is the Jones oxidation. And the Jones reagent is a combination of one of 2 chromate salts, so either sodium dichromate, Na2Cr2O7, or potassium dichromate, K2Cr2O7, with sulfuric acid. These, either sodium dichromate and sulfuric acid or potassium chromate sulfuric acid, these come together to generate chromic acid, right, which is going to be CrO4H2, right? Now, I don't need you to know arrow pushing for the Jones oxidation, but I do need you to know kind of what types of products come out. So if we have a primary alcohol, right, so this is a primary alcohol, under Jones conditions, we will form a carboxylic acid. We can't stop at the aldehyde. This is Jones conditions. We'll take a primary alcohol all the way to the carboxylic acid. If I have a secondary alcohol, Jones conditions will take that to the ketone. Whoops. Can't start from a ketone. Excuse me. A secondary alcohol under Jones conditions will take us to a ketone. A tertiary alcohol we get no reaction. And if we start with an aldehyde, Jones conditions will also take us to a carboxylic acid. Okay? So this is what I need you to know for the Jones, right? Be able to tell me what products form from what types of starting materials, or be able to fill in reagents. So that's the kit and caboodle for the Jones oxidation, right? What we're going to do is we're going to come back and we're going to look at a related oxidation known as the PCC oxidation, pyridinium chlorochromate, and for that one we are going to need to know the mechanism. So we saw just a moment ago that a Jones oxidation takes a primary alcohol all the way to the carboxylic acid. Well, as chemists, we like to have a degree of control, And we'd like to be able to stop that, instead of going all the way to the carboxylic acid, we'd like to be able to stop it at the aldehyde and be able to take a primary alcohol to an aldehyde. And we can do that using what's known as a PCC oxidation, right? So PCC is pyridinium chlorochromate. Excuse me, let's just draw that a little bit more clear. So there's our pyridinium. We have a chlorine ion to balance our salt. And we have chromate, which is CrO3. Now, these two species, this pyridinium chloride salt and our chromate, our chromium oxide, chromate, right? These are in an equilibrium where the chlorine ion actually attacks into the chromium to give us a species that looks like this. Right, so there's our PCC equilibrium. And now we can bring in a primary alcohol and begin our reaction. And so in the first step of our reaction, our alcohol oxygen attacks into the chromium center, displaces the chlorine ion. From there, we have this intermediate, right? We have our pyridine, or I should say more appropriately, our pyridinium, and we have our Cl- still. The negatively charged oxygen on the chromium deprotonates the pyridine, there's our chlorine ion. It now gets to balance the charge on oxygen. Our pyridine can come along and deprotonate that oxonium. I'm going to work up just a little bit, give myself some more space. Now I'm going to draw in those hydrogens for my oxygen atom, right? And we've got another double bond O there, and we've got an OH here. And so now, what can happen is essentially an intramolecular E2 reaction, right? We need to think E2 at the end. That's how we get this to go down. And if we look at the arrow pushing that happens, I have something that can act as a base, removing a proton while simultaneously expelling that chromium leaving group and creating the new carbon-oxygen double bond. That now takes my primary alcohol to an aldehyde. I have my chromium right? And I have my pyridinium chloride at the end of the reaction. Okay, so this is known as a PCC oxidation. It's a really powerful way for us to be able to convert primary alcohols into aldehydes. But the issue is that we are using chromium-6, right? Chromium-6, hexavalent chromium, is, again, it's right in the ballpark of osmium tetroxide. These are some seriously, seriously bad chemicals for your health, right? You get cancer, lung issues, all kinds of problems, right? So we'd like to avoid using these transition metals or these toxic metals whenever we can. And so this is going to bring us to our last and final mechanism, right, for topic 26, the Swern oxidation, which is my favorite mechanism in all of Chem 201. I love the Swern oxidation mechanism, and that should be a big hint to you as you're studying through redox reactions. Sam loves the Swern. Okay, so I'm going to clear off the board, and we're going to come back and we're going to take a look at the Swern oxidation, how we can convert a primary alcohol to an aldehyde without using any metals whatsoever. All right, so give ourselves plenty of space. The Swern oxidation. Now, the Swern oxidation, like I said, is a method by which we can convert a primary alcohol into an aldehyde. But instead of PCC, where we have to use chromium, right now we're going to be able to do this without using any metals at all. And we're going to use a couple of different reagents. One of them, oxalochloride. And with that, we're going to need some dimethyl sulfoxide. These two reagents are added to our alcohol in our first step. We let them do their job, and then afterwards we add in triethylamine. And out the other side, we'll get our aldehyde, all in one reaction vessel. We just got to give oxalochloride and DMSO a chance to do their job first. So, as I've said, I love this mechanism. It's my favorite mechanism in all of Chem 201. So let's go through and see just how exactly does the Swern oxidation, what's our electron pushing to make this happen. So in the first step of the Swern oxidation, DMSO acts as a nucleophile and attacks into one of these carbonyl carbons to generate our first intermediate. Okay, and now the positive charge on our oxygen is going to come down to reform a carbon-oxygen double bond and kick out one of those chlorine atoms. Here, our next step, our chlorine atom that we just kicked off is going to come and attack at the sulfur atom. And so I'm going to move that positive charge just so that we can see the arrow pushing a little bit more clearly. So the chlorine, right here are our electrons on oxygen, the chlorine attacks at the sulfur atom. That's going to break the sulfur-oxygen bond, which is going to form an oxygen-carbon double bond. That is going to break our carbon-carbon double bond. Those electrons are going to fall onto the carbon, and that's going to push out the other chlorine. And what we find in the end is we have generated sulfur is now single bonded to one of those chlorine atoms. it still has a positive charge on it. This oxygen, this carbon, and this oxygen all come together to make CO2. This oxygen and this carbon atom come together to make CO. And finally, this chlorine gets kicked off as an anion, which is going to hang out with our positively charged sulfur to balance everything out. From here, our alcohol can now finally begin to participate. So here now, our primary alcohol. You can also do this with secondary alcohols to form ketones. I'm showing it with the primary alcohol to form aldehydes. Tertiary alcohols don't undergo oxidation. Okay, so now our oxygen of our alcohol attacks into sulfur, which kicks off that chlorine atom. That takes us to this intermediate. Excuse me. There's nothing there, right? We got a pair of electrons on that oxygen atom, and we have a chlorine there and another chlorine hanging out as well. Two positive charges. We haven't lost any chlorines to anything just yet. Now, one of these chlorine atoms is going to act as a base to deprotonate our oxonium. We're going to make HCl there. And so we still have a Cl minus. And now this acid-base equilibrium is going back and forth, back and forth, back and forth, back and forth, back and forth. However, it is at this stage that we bring in our second reagent, triethylamine. And we're going to use excess triethylamine for two reasons. One, we want this equilibrium to stop happening between HCl and oxonium, and so one equivalent of triethylamine reacts with HCl to give us this salt. And now that hydrogen on the nitrogen has a pKa of 10 versus a pKa of negative 9-ish or a pKa of negative 2. And so this then shuts down that HCl from being able to keep this equilibrium going back and forth. From there, a different equivalent, right, a different molecule of triethylamine is able to deprotonate the methyl group, right, on that sulfur. One of the methyl groups on that sulfur. And so now we have this situation here where I've got a negative charge on this carbon atom and 1, 2, 3, 4, 5 atoms away I have a hydrogen. This is a deprotonation that's actually exceptionally favorable. Again, this is an E2 style elimination, if you think about it, because simultaneously, while I'm grabbing that hydrogen, I'm going to kick off a leaving group. That's going to leave me with my aldehyde, and I've reprotonated that carbon atom, and I've made dimethyl sulfide at this point. And so one of the other reasons I really like the Swern oxidation is even though dimethyl sulfide smells terrible, absolutely horrible, right? If you add in your triethylamine and you begin to smell that terrible smell of dimethyl sulfide coming from your reaction, we used to call that, when I was in grad school, the sweet smell of horrible success, right? That dimethyl sulfide smell tells you that your reaction worked. And you got to do your oxidation without exposing yourself to any toxic metals. Okay, so Swern oxidation, by far my favorite mechanism in all of Chem 201. So that's going to wrap it up for redox chemistry, right? That covers topics 25 and 26. Again, I would recommend, as I did at the end of topic 25, make yourself a reaction list, see the different reactions that were covered here, which ones you're expected to know arrow pushing, and which ones you can let the arrow pushing go on. As always, if you have any questions, please come by, see me during office hours, bring your questions to lecture or conference, or make an appointment to see me one-on-one. Thank you for your time.